Hello, everyone. This is Asim Ghalib, a PhD candidate at the University of British Columbia, Canada. Today, I'll be presenting our paper, eTainter, Detecting Gas-Related Vulnerabilities in Smart Contracts. This work is a joint work with my PhD at Pfizer, Julia Robin, and Karthik Bhattacharya. So let's start our presentation by a brief introduction about smart contracts. Recently, smart contracts have been adapted in several sectors, such as finance, gaming, and actually there are several use cases of smart contracts, such as the distributed finance, the non-fungible tokens. In the current days, Ethereum is the most popular blockchain platform for running smart contracts, and we can see that smart contracts hold nearly 23% of Ethereum supply, which is about 32 billion as of June 2022. This financial nature of smart contracts unfortunately provides a good incentive for attackers to target smart contracts for financial gain. For example, several attack incidents targeted smart contracts over the past few years, and these attack incidents actually resulted in the loss of millions. In a high level, smart contracts are basically small programs running on top of a blockchain. They are written in high-level languages such as Solidity, and then they are compiled to low-level EVM bytecode that is deployed on the blockchain. In smart contracts, actually, there is no single entry point of execution, and every public or external function in the contract is an entry point. For example, in this contract, users can call by ticket function or pick the winner function. And unlike traditional programs, the execution of smart contracts actually costs gas. We can think of the gas cost here as energy consumption. Actually, there is a gas cost for every low-level instruction in the bytecode. And this gas cost is actually paid by the caller of the contract. So when a user calls a contract, they specifies the function they want to call and also the maximum gas they want to spend on executing this function. So when a user submits a transaction, the contract code keeps executing as long as there is enough gas for running the code. So what happens when the user doesn't provide enough gas for running the transaction? In these cases, the transaction actually will run out of gas, execution halts, and then the changes made to the contract state by the transaction will be rolled back. On the other hand, transactions cannot consume unlimited gas. The amount of gas that can be spent on executing a transaction must be less than the block gas limit set by Ethereum. So during the execution of the contract, if the gas cost actually exceeded the block gas limit, then the changes made to the contract state will be rolled back as well. So the dependency of on the gas concept actually to execute smart contracts can result in several vulnerabilities in the code of the smart contracts. The contract actually may contain code patterns that increase the gas cost of the contract. And these code patterns may get used by attackers to force unwanted behavior on the contract, such as a launching denial of service attack on the contract. The governmental contract is a good example here, where about 2.5 million were locked out in this contract just due to a loop that exceeded the block gas limit. And also, actually, we see such vulnerabilities frequently reported by security practitioners. So to address this problem, the purpose of our work is to enable developers, security auditors, and smart contract users to discover and find gas-related vulnerabilities in smart contracts. So let's see examples of the gas-related vulnerabilities that actually can exist in smart contracts and that we are targeting in our work. For example, in this contract, this for loop is bounded by a dynamic array. So if the attackers actually can control the size of this array, they will be able to force the execution of pick winner function to exceed the block gas limit and then perform denial of service attack on this contract. Also, we have the external call transfer is executed within the loop body. So if the attacker can make themselves a target for this external call, they can actually force this loop to run out of gas and fail just by increasing the gas cost of the code executed on the target side of the external call transfer. For the related work on detecting gas-related vulnerabilities, MadMax was the first work to define and detect gas-related vulnerabilities. But MadMax actually uses predefined rules that are based on specific code patterns. So any variation in these code patterns makes MadMax fail. In addition to that, MadMax report high false alarms. For example, for MadMax to detect this unbounded loop, it checks if the loop is bounded by array size variable, and it actually fails to infer the array size variables when the arrays are nested in other data items, as it is the case in this example. So our goal in this work is to build an effective approach to find gas-related vulnerabilities in smart contracts. Our observation in this work is that we found that actually gas-related vulnerabilities are caused due to the dependency of the contract code on data sources that can be manipulated by the contract users. So based on this observation, actually, we see that gas-related vulnerabilities can be detected by tracking TINs without the need for any existing rules. So the key area in our work is to track TINs into the code patterns that can increase the gas cost of the smart contract. So let's have a quick look at the workflow of our approach. The approach takes as input the bytecode of the contract. And by working on the bytecode of the contract, this increases the scope of the contract that can be analyzed by our approach, as only the bytecode of the contracts is available on the Ethereum blockchain. It then builds the control flow graph and finds the sources of TINs in the code. And also, it also finds the statements that can cause gas-related vulnerabilities in the code. So, and then identifies these statements as sinks for the TINT analysis. After that, the approach performs TINT analysis to find gas-related vulnerabilities. And in some cases, developers may write code patterns to protect the existing vulnerabilities from being exploited by attackers. And for our approach to optimize for high precision, it actually analyzes for such protection patterns. Finally, the approach will report the found vulnerabilities in addition to the statements or the functions that can be used by attackers to exploit such vulnerabilities. Tracking TINs in the contract bytecode to detect gas-related vulnerabilities actually is a challenging problem. The bytecode actually has several patterns of use. For example, loops used to handle operations on strings that are represented as dynamic arrays. And here we need to distinguish this kind of loops from loops that can lead to gas-related vulnerabilities. In addition to that, unlike traditional programs, contracts can actually store data permanently in the contract storage on the blockchain. So TINs may propagate throughout the contract storage. And also Ethereum uses cryptographic hashing to access dynamic items in the contract storage, such as arrays. This makes tracking TINs or propagating TINs statically in the bytecode challenging. So let's see in this example how TINT analysis can be used to detect the unbounded loop at line 15. At first, the approach will use the exit condition of the loop as a sink for the TINT analysis. It will then find the sources of TINs in the code. For example, here message to sender, and that returns the color of the contract, and also bit price and when prices are sources of TINT because they are parameter of public functions. Then the approach will find that a data value loaded from storage is used in the loop exit condition. So the approach initially will consider this storage location as a source of TINT. but it needs actually to validate that or check that users can actually write or manipulate this storage location. For this reason, it will use this storage location as a sink for the tent analysis. It then performs tent analysis, and it finds that tents are reaching to this storage location. So it will mark this storage location as tinted, and it will also confirm this storage location as a source of tents. Finally, the approach will report this loop as unbounded loop because tents are reaching the exit condition of the loop that is defined or that is used as a sink for the tent analysis. We evaluated our approach actually by answering 3 main research questions. In the first research question, we evaluated the effectiveness of our proposed approach eTainter compared to MadMax. And in the second research question, we evaluated the performance of eTainter in terms of the analysis time and the use memory. And in the third research question, we studied the prevalence of gas-related vulnerabilities in the wild. So to answer the first research question, we used annotated data set of about 28 contracts. 8 of these contracts were used by MadMax paper to evaluate the precision of MadMax. So we inspected these 28 contracts manually and then annotated the existing vulnerabilities as a ground truth to evaluate the effectiveness of eTainter and compare it with MadMax. Then to evaluate the performance of eTainter, we used Ethereum dataset. This dataset consists of 60,000 unique smart contracts, and we extracted these contracts from Ethereum blockchain. And also to study the prevalence of gas-related vulnerabilities in the wild, we used Ethereum dataset and another dataset, which is Babylar contracts dataset. This dataset consists of 3,000 contracts that have the most or the largest number of transactions on the Ethereum blockchain. So let's see or discuss the result of our evaluation. From the result, we found that our approach actually was able to find more vulnerabilities and reported few false positives compared to MadMax. Actually, our approach achieved both high precision and recall, where the precision was 90% and the recall is 94, comparing to 64 precision and 74 recall for MadMax. So here we find that eTainter achieved better recall and precision than MadMax. And in the second research question, we found that the average analysis time of our approach is 8 seconds, and also the average memory is 118 megabytes. We found that our approach has a practical analysis time. It was actually able to analyze 97% of the successfully analyzed contract in just less than 1 minute each. So finally, by running our proposed approach eTainter on the Ethereum dataset and the Babylar contract datasets, eTainter was able to find gas-related vulnerabilities in about 2,700 contracts in the Ethereum dataset. It also was able to find vulnerabilities in 70 contracts in the most frequently used contracts. Hence, we can see that gas-related vulnerabilities are prevalent in both datasets and also hence are prevalent in the wild. To summarize, in this work, we have proposed eTainter for detecting gas-related vulnerabilities in smart contracts based on the use of tent tracking without the need for any existing rules. From the evaluation of eTainter, we found that eTainter achieved both high precision and recall better than MadMax. And also we found that gas-related vulnerabilities are prevalent in the wild. We made eTainter code and the use dataset available online, and they can be accessed using this link. This comes to the end of my presentation, and I'm happy to answer your questions. Thank you.